Okay, so let's see how this goes. Today we're going to talk about compounds and molecules, and we're also going to talk about bonding. So the first thing here you can see from your notes is we're going to talk about the difference between a compound and a molecule. One thing to remember and try to keep straight is that they are both made through bonding of atoms. So therefore the statement here, both are chemically bonded, is what that means. So we have atoms that are bonded together. And maybe we should clear up that how the bonding occurs. So we're going to make compounds and molecules by using electrons. So bonds are created through the electrons. Okay. Most of the time when we're talking about just compounds, let's make a little chart down here that gives us the difference between compounds and molecules. Most of the time when we're talking about just compounds, we're usually talking about 2 atoms at most. Okay, when we're talking about molecules, we could be talking about 3, 4, up to hundreds of atoms together. And one of the things we're going to focus on later in this chapter is actually things that are called macromolecules. That would be those molecules that are hundreds of molecules large. However, one of the other things that stipulates the difference between a compound and a molecule is usually compounds are very simply bonded. Meaning they're strictly either ionic or covalent. Molecules, on the other hand, they can be mostly covalent, then you can have other types of bonds for example, hydrogen bonds, which we'll get to in a couple classes, or those other types of forces that we were looking at in vocab, the van der Waals forces, get involved when we're looking at these bigger molecules. Okay, so what we have actually pictured there is one of those bigger molecules. That happens to be the molecular diagram of caffeine in your notes there. And as you can see, there's some nitrogens involved, there's an oxygen or two involved, there's double lines. When you see a double line, it represents a double bond. So this here is a double bond. Whereas the single line, like this one here, is just a single bond. So in a double bond, you have 4 electrons involved. And in a single bond, you have just 2 electrons involved. Okay, the last thing I want to talk about on this particular slide is this little mnemonic device we have here. You can pronounce it as it is written there. It would be pronounced Vichfon. It's our little pneumatic device for what we use to remember what we call a diatomic molecule. Okay, I'm going to pop this up here just so that we have space. Diatomic molecules exist naturally as paired atoms. And these symbols are the atoms or the elements that exist this way. So, for example, boron is one of them. Iodine is another one. So you would have B2, I2, Cl2, H2, F2, O2, and N2. So you'd have boron, iodine, chlorine, hydrogen, fluorine, oxygen, and nitrogen as your diatomic molecules. They exist in nature paired together. So it becomes important when we look at balancing equations and writing chemical reactions and trying to decide what are the outcomes of the reaction or what went into the reaction, if these are involved. Because if you're using oxygen as part of the reactants of the equation, then you have to recall that when you write oxygen, it's O2 and not just O. Okay, let's flip to the next page. Oh, hang on a second. We're having technical difficulties with the paper there, guys. Okay, so the first type of bonding we're going to talk about is ionic bonding. And in a day or so, we're going to do a sheet that we're going to put into your resource section that will allow you to have this kind of information condensed all in one spot so that you'll always have it in your resource section. But for right now, we're just going to focus on doing the notes for it. So the first type of bonding is going to be ionic bonding. And there are a couple of things you need to know that are key to ionic. Okay, the first thing that you need to make sure that you understand happens in an ionic bond is that we're always going to be dealing with a metal and a nonmetal. So for example, in the sample that we have over here in the diagram, we have sodium, which is our metal. Remember that metals live on the left side of the periodic table. And then we have our nonmetal over here, chlorine. Remember that chlorine or the nonmetals live on the right side of the periodic table. Okay, so this is going to make us sodium chloride, which is very simply table salt. So table salt and salts in general, salts like you put on your walks in the wintertime to thaw the ice, salts like you use for pickling, salts that you use for baths or for, you know, having a salt scrub or something like that. They are all ionic bonds. So they're going to happen between a metal and a nonmetal. The second key to understanding ionic bonds is that the metal will always give up its electrons And the nonmetal will always take them on. Okay, so we kind of talked about this the other day a little bit when we talked about what an ion is. And we said that ions are made when an ionic bond dissociates or breaks apart. So when we're first looking at a nonmetal and a metal and looking at whether or not they will bond, we're going to take into consideration what happens or what is happening in their valence orbital or their valence shell, that outermost shell. How many electrons are in that outer shell? And we're going to do an exercise in a day or two where we're actually going to see that that outer shell is really what's most important, because underneath that shell, right here, for example, and right there, for example, you have an orbital that's full. You should recall from your homework, you had a question that asks, how many electrons can you put into each of the shells? And for the amount of elements that we're going to use, you're really not going over maybe the second, maybe the third shell. Once you get past that, it gets kind of tricky, and I'm going to leave that to the chemistry teachers to describe to you as to why, and it has something to do with the distance away from the nucleus that those shells are floating, or the orbitals actually exist. And it has to do with then what the electrons are capable of doing between those shells that are out there. So we'll leave that up to the chemistry teacher. Okay. Our important thing to remember is that if we were to take a look at the number of electrons in sodium's outer shell, we would see that there's only one right there. And if sodium could get rid of that electron, then his outermost shell, that one that lies beneath there that we're pointing to, that shell would be full. Take a look at chlorine's on this side. He has 1, 2, 3, 4, 5, 6, 7 electrons in his outermost shell. If he could just get one more electron to fill the spot right there, then his outermost shell would be full. This is why this type of bond works between this metal and this nonmetal. Okay, so this type of ionic bond that is formed happens because sodium gives up his electron to chlorine. And that gives us the bond between Na and Cl, written like that. Usually, if you're asked to demonstrate an ionic bond, we use what's called a Lewis dot. And in your homework, you had practice for both Bohr models and Lewis dot structures. Lewis dot structures involve just the electrons in the outermost shell. So I'm going to pull this out over here. Sodium would have only the one electron in its outermost shell, and chlorine would have 7. And the way we demonstrate that an ionic bond is forming is we draw an arrow. So you would indicate the direction that the electron is going. We can clear this up when I get back and do a couple of practices from your homework and things like that, and talk a little bit more about ionic bonding and what is really happening and how to represent the different types of bonds that can happen in ionic bonding. The last thing to remember that's key to an ionic bond is that if you break them, you don't get sodium back and you don't get chlorine back. when you break an ionic bond, you're only going to get the sodium cation and the chlorine anion. So when you break those bonds, that's what you're going to get. Okay. Last type of bonding we're going to talk about today. Most of the molecules that we're going to discuss for the rest of the school year are going to be covalently bonded. They're going to have all kinds of crazy other bonds going on as well, including hydrogen bonds and some of those van der Waals forces and some other types of bonds that we'll talk about, peptide bonds and things like that, when we get to those other bonds. But even those bonds are essentially a type of covalent bond. So in a covalent bond, what's different is instead of one atom giving up the electrons and one atom taking on the electrons, the atoms share electrons. So in a covalent bond, most of the time you're not going to see metals. Most of the time, who you are going to see are nonmetals. Again, we say most because every now and then there's somebody who doesn't follow the rule. But most of the time you're going to see only nonmetals. Okay, so in our diagram here in your notes, we have two of the diatomic molecules, which are covalently bonded to each other, and we have good old water. In this example, we have hydrogen, and in each hydrogen atom, there is one electron floating around in that outermost shell. If hydrogen was to share his electron with this hydrogen, then each would have two electrons in its outermost shell. And the way that works is if this is hydrogen's, and I'm going to draw his proton nucleus blue to match the electron. If this hydrogen decides to share his electron with this hydrogen, then some of the times that electron is floating around that hydrogen, and then some of the times the electron is floating around this one. Some of the time it's around this one. Some of the time it's around this one. The same can happen for this hydrogen. So we'll make that electron there red, not the greatest, but to match that hydrogen's nucleus. And again, some of the times it'll be floating around this one, and some of the times it'll be floating around this one. That's why we say that they share them, because they're spending equal amounts of time around each other's nucleus. In oxygen, we have 4 electrons that are going to be shared. Here are the 4 that are going to be shared, because oxygen has only 6 electrons. So 2 from each will have to be shared. Because 2 from each are shared, notice that there's a double bond between oxygen atoms. Okay, our last example is water. And as you can see, here's oxygen's 6 electrons, 1, 2, 3, 4, 5, 6. And each hydrogen has one. And when they create the covalent bond between them, sometimes hydrogen is spending time around oxygen's nucleus, and sometimes hydrogen's electron is spending time around his nucleus. Same thing goes for this one. This is going to create a very different situation, which we're going to spend another class period talking about how these types of covalent bonds impact how water reacts. But for today, we just need to make sure that you understand that water is covalently bonded. Okay, so now you have enough information to start practicing the bonding of atoms. If you're going to do sharing of electrons, notice there's no arrows. Instead, we use lines to represent bonds, unlike in the ionic where we had arrows directing which way the electrons went. All right, you should be good to go to try to do your homework. Remember, it's okay if you're not getting it. We'll take the time to review, but just make sure you make an effort to do it.